Hi, so let's talk now about binary search. A dictionary is a good example of a ordered list, okay, basically where every word is in order, and that makes finding words much easier. You can imagine how difficult it would be to search in a dictionary if the order of the words was random, right? You'd have to just search through every single page and in fact every word on every page. That would take quite a long time. So let's look at the problem statement for searching the sorted array. So what we have coming in is an array, along with a low and upper bound that specify the bounds within the array in which to search. What's important about the array is that it's in sorted order. What we mean by that is if we look at any index I at an element, and then the next element, that this first element is no more than the next element. We don't say less than, because we want to allow for arrays that have repeated elements. So officially this is called a monotonic, non-decreasing array. The other input is the key to look for. The output for this is an index such that the element at that index in the array is equal to the key. We say an element and not the element, just as we did in linear search, because of the fact that there may be more than one element that matches, because there may be duplicates in the array. If we don't have a match, instead of returning not found as we did in the linear search case, we're going to actually return somewhat more useful information, which is where in the array would you actually insert the element if you wanted to insert it, or where would it have been, okay, if it were there. So what we're going to return is the greatest index such that a sub I is less than k. That is, if the key is not in the array, we're returning an index such that if you look at the element at that index, it's less than the key, but the next element is greater than the key. And we do have to take account of the fact that what if every element in the array is greater than the key? In that case, we're going to go ahead and return low minus 1. So let's look at an example. We've got this array with 7 elements in it, and the element 20 is repeated in it. So if we search in this array for 2, we want to go ahead and return 0, saying that every element in the array is larger than this. If on the other hand we look for 3, we're going to return 1. If we look for 4, we're also going to be returning 1, which really signifies between 1 and 2. That is, it's bigger than 3, but it's less than 5. If we search for 20, we'll return 4, or we might also return 5. Either one of those is valid because 20 is present at each of those indexes. And if we search for 60, we'll return 7, but if we search for 70, we'll also return 7. So let's look at our implementation of binary search. So we're going to write a recursive routine taking in a, low, high, and key, just as we specified in the problem statement. First, our base case, right? If we have an empty array, that is if high is less than low, so no elements, then we're going to return low minus 1. Otherwise, we're going to calculate the midpoint. So we want something halfway between low and high. So what we're going to do is figure the width, which is high minus low, cut it in half, so divide by 2, and then add that to low. That might not be an integer because of the fact that high minus low divided by 2 may give us a fractional portion. So we're going to take the floor of that. For example, in the previous case where we had 1 to 7, it'll be 7 minus 1 is 6, divided by 2 is 3, plus our low is 1 is 4, so the midpoint would be 4. We'll see an example of this shortly. And now we check and see, is the element at that midpoint equal to our key? If so, we're done, we return it. If not, the good news is, of course, is we don't have to check all the other elements. We've ruled out half of them. So if the key is less than the midpoint element, then all the upper ones we can ignore. So we're going to go ahead and now return the binary search in A from low to mid minus 1, completely ignoring all this stuff over here. Otherwise, the key is greater than the midpoint, and again we can throw away the lower stuff and go from midpoint plus 1 all the way to high. Let's look at an example. So let's say we're searching for the key 50 in this array with 11 elements. So we'll do a binary search on this array from 1 to 11, looking for 50. Low is 1, high is 11. We'll calculate the midpoint. The midpoint will be 11 minus 1 is 10, divided by 2 is 5, Add that to 1, the midpoint 6. And now we check and see, is the midpoint element equal to 50? Well, no, the midpoint element's 15, and the element we're looking for, the key we're looking for, is 50. So we're going to go ahead and ignore the lower half of the array and now call binary search again with the low equal to 7. So one more than the midpoint. So now I've got a smaller version of the problem. We're looking for 50 within the elements 7 to 11. We'll calculate the midpoint. 11 minus 7 is 4. Divided by 2 is 2. So we'll add that to 7 to get a midpoint of 9. We check, is the element at index 9 equal to our key? The element at index 9 is 20. Our key is 50. They're not equal. However, 50 is greater than 20, so we're going to go ahead and make a new recursive call with midpoint plus 1, which is 10. So again, we do our binary search from 10 to 11. We calculate the midpoint. High minus low, 11 minus 10 is 1, divided by 2 is 1/2, plus 10 is 10.5. We take the floor of that, we get 10.5, so our midpoint is 10.5. I'm sorry, our midpoint's 10. And now we check, is the value at element 10 equal to our key? Well, the value at element 10 is 50, our key is 50, so yes. So we're going to go ahead and return that midpoint, which is 10. In summary then, what we've done is broken our problem into non-overlapping subproblems of the same type. We've recursively solved the subproblems, and then we're going to combine the results of those subproblems. Okay? We broke the problem into a problem of size half, even slightly less than half. We recursively solved that single subproblem, and then we combine the result very simply just by returning the result. In the next video, we're going to go ahead and look at the runtime for binary search, along with an iterative version. And we'll get back to actually discussing that problem that I discussed with the dictionary translation problem. We'll see you shortly.